Welcome to Precalculus Lesson 2, Graphs of Functions. You can look at section 1.2 in the textbook for more information on the content here. And this is Ruth Trigstad, your instructor. Let's go ahead and get started with intercepts. Suppose a graph of an equation is given, as we have here. A point on the graph that is also on the x-axis is called an x-intercept of the graph. So the x-intercepts on this graph are negative 5, 0 and negative 1, 0. Note that they're points, not numbers. A point on the graph that is also on the y-axis, like right here, is called a y-intercept of the graph. So again, the y-intercept is the point 0, negative 7/4, which is a bit of an approximation, but good enough. The toolkit functions are the next important thing we're looking at in here, also called the parent functions. These are the basic functions that we'll use in this course for transformations and for creating piecewise defined functions, like we'll do in just a few minutes here. Y equals 2 is our first parent or toolkit function. This is referred to as a constant function. Really, the constant function is y equals c, where c can be any real number, but in this case I threw in 2, so it makes a little more sense for sketching a graph here. This is y equals 2. The domain here, as you can see, is all real numbers, all x values. The range includes only the one y value of 2, and so the range goes from 2 to 2, which we can indicate in interval notation with square bracket 2, comma 2 square bracket. There's one intercept here at the point 0, 2, and so the intercept is the point 0, 2. There are no y-intercepts. I'm sorry, that is a y-intercept. There are no x-intercepts here. Okay, next we have y equals x, the identity function. This is an important function we use quite a bit in this class. The domain, all real numbers. The range, all real numbers. The intercepts, there's only one intercept. Both the x and y intercept here is the point 0, 0. Y equals absolute value of x is referred to as the absolute value function. You can see here the domain includes all x values. The range starts at y equals 0 and includes also all positive y values past that. So the range goes from 0 to infinity, including 0. The intercepts, there's only the one intercept of 0, 0. Next we have y equals x squared. This is the squaring function. The squaring function is next to the square root function. This is probably the function we use the most in here for examples. So let's put a few points on our graphs. The key points here that we usually use when graphing or transforming this graph are 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. All right, and the domain, if we smash this graph down onto the x-axis, it would keep going on forever in both directions. The domain is all real numbers. The range starts at 0 for y values and includes all positive numbers, 0 to infinity. The intercepts, there's only one, and that is a point 0, 0. Next we have y equals x cubed, the cubing function. Looks like so. You could graph points on this. Some nice points to plot would be letting x be equal to negative 2, negative 1, 0, 1, and 2, and finding those y values that correspond to those particular x values. The domain is all real numbers. The range is all real numbers. The intercept is 0, 0. Y equals 1 over x, an interesting function. This is the reciprocal function that looks like so. I would practice plotting some points and graphing this on your own. If we look for the domain here, notice that if we were able to smash this graph from both directions onto the x-axis, the only missing point there would be 0. And so our domain is from negative infinity to 0, union 0 to infinity. Same thing with the range. If we smash the graph horizontally from both directions onto the y-axis, we would be missing y equals 0. So our range would be negative infinity to 0, union 0 to infinity. There are no intercepts. So although the graph gets really close to the x-axis and to the y-axis, it never touches either of those. So no intercepts here. Y equals 1 over x squared is the reciprocal squared function. It's similar to the reciprocal function, except that because we square our x here, all of the y values are going to be positive. So our domain here would be negative infinity to 0, union 0 to infinity, just like the reciprocal function. However, the range starts above 0 and goes from 0 to infinity. The intercepts, there are none. And we move on to the square root function. As I mentioned, this is an important function. Let's do a few key points here. 0, 0, 1, 1, 4, 2. Keep those points in mind throughout the course. The domain, here we start at x equals 0 and go to the right, to the positive side. From 0 to infinity is the domain, including 0. Same with the range, 0 to infinity, including 0. We have the 1 x and y intercept of 0, 0. Y equals cube root of x, the cube root function. This is not used all that much in this course, every once in a while, but it's used a lot in calculus, so it's good to get used to seeing it. The domain, negative infinity to infinity. Range, negative infinity to infinity. Intercepts, that one intercept of 0, 0. Piecewise defined functions. We're going to use these parent functions to graph at least one of these. I'll do one and I'll let you try one on your own. So here we're going to graph the piecewise defined function f of x equals absolute value of x if x is less than or equal to negative 2, 3 if negative 2 is less than x is less than 1, and 4 minus x if x is greater than or equal to 1. So let's start with looking at f of x equals absolute value of x. And here we have that graph. We're only interested in the part of this graph where x is less than or equal to negative 2. So right here on my graph, I'm going to put a dot where x equals negative 2. And then we're wanting x values less than that. So we want just this one little part of this, what we call a subgraph, to create our final graph here. And I'll transfer the red part that I've sketched in over to the main graph. Here we start at negative 2, 2, and we copy the red part of our graph here. We go to the left and up, and then we move on to our next function, which is f of x equals 3. I've sketched that here. And this part of the graph, we want negative 2 less than x less than 1. So we're not going, because we don't have an equals with the less than signs here, we're not going to include x equals negative 2, and we're not going to include x equals negative 1. We'll put open circles at both of those points on this graph, meaning the points are not included. But we do want all the points between those two numbers. And so let's transfer over here. So we have the point negative 2, 3, and we have the point 1, 3, and we'll put a line segment between those two open circles there. And we move on to our third part of this graph. Right here, f of x equals 4 minus x. So right here we have y equals 4 minus x. I've already sketched it, but if you wanted to plot this on your own, remember it helps to find a couple points on the graph. If we let x be equal to 4, y would be 0. If we let x equal 0, y would be 4. And so if I plot the points 4, 0 and 0, 4, they give me this graph. For this third subgraph, I only want the part of this graph where x is greater than or equal to 1. So I start by putting a dot on my graph. at the point 1, 3, it looks like. And I want everything bigger as far as x values go. So I want everything to the right of that point. And I'll take this point, transfer it over here, 1, 3. Notice we're filling in the hole we had here at 1, 3. And then we go down to the right. I kind of went off track there, but there we go. So the final graph should look something like so. And if you wanted to, you could do a different color there. You could like take a black marker and put everything in black so it looks like it's all the same graph there. Okay. Yeah, I kind of messed up that one, but anyway, you get the idea. So I'm going to have you do your own for the first try on your own problem today. Graph the following piecewise defined functions. Stop the video for a minute if you need to write this down. F of x equals x squared. If negative 2 is less than or equal to x is less than or equal to 1. F of x equals square root of x if 1 is less than x is less than 4. F of x equals 6 minus x if x is greater than or equal to 4. So give that a try. We're going to look next at symmetry. 2 points A, B, and CD in the plane are said to be symmetric about the x-axis if A equals C and B equals negative D, as in this first sketch here. So here you can see that A equals C and B equals negative D, or D equals negative B. And this graph is symmetric about the x-axis. You can also see that the top half of the graph is a mirror reflection across the x-axis to give you the bottom half of the graph. A graph is symmetric about the y-axis, as right here, if A equals negative C, or that would mean that C equals negative A, and if B equals D or D equals B. So we have 2 points on our graph there. And for a mirror reflection of this graph across the y-axis, you can kind of get a visual of that. If you imagine taking this left half and flipping it across the y-axis, it gives you the right side there. Finally, we have a graph that's symmetric about the origin. To tell if a graph's symmetric about the origin, we need to test that A here, if we should have 2 points in the graph where A equals negative C, or C equals negative A, and where B equals negative D, which means that D would equal negative B. So that's the setup. This is symmetry. We're not going to do a whole lot with symmetry here, but we use symmetry in this course I should mention, to determine if a graph is symmetric about the origin. And this doesn't verify it. It just kind of to guess if a graph is symmetric about the origin. We can look at the graph, and if we imagine rotating that graph 180 degrees, we should still have the same graph that we started with. Okay, well, we're using symmetry to determine if functions are even and odd. In this last example, we actually don't have graphs of functions here. We have graphs of relations. But from now on, we'll only have graphs of functions, at least for this part of the course. So we're going to look at a function f being called even if its graph is symmetric about the y-axis, and odd if its graph is symmetric about the origin. So we just looked at symmetry about the y-axis, symmetry about the origin. Here we have an example of a graph that's symmetric about the y-axis. So if a graph is symmetric about the y-axis, we're told that this is the graph of an even function from the definition here. And I'm going to work with this just a little bit more to get some more information here. So if I have the point AB on this graph, and we'll say this is the graph of y equals f of x, then for any point x I have in the graph, I can think of A as being equal to x, B as being equal to f of x. Okay, anytime we have a graph y equals f of x, if we plug x into our function, we get f of x. Okay, so we'll rewrite AB as the point x f of x. That would mean that the point negative AB would be the point negative x. And if we plug in negative x to f of x, we would have f of negative x. So the point negative AB we're going to think of as being the point negative x, f of negative x. Well, we can see here that b equals b, right? These are the same y values. And if b equals b, that tells me that for an even function, it has to be true that f of negative x is equal to f of x. Okay, so that's going to be our test. To determine if a function is even, we want to test on whether f of negative x is equal to f of x. And if that is the case, then my function is even. This is an analytic approach to determining if a function is even or odd. Next, we look at the graph of a function which is symmetric about the origin. So this graph from the previous slide we were looking at, you can refer back to that. This graph is symmetric about the origin. That tells me that the function represented by this graph y equals f of x, the function is odd. Okay, I know the function's odd because my graph is symmetric about the origin. Let's, from this, figure out how we could do an analytic algebraic test to determine if a function is symmetric about the origin or if a function is odd. Well, if I take my point AB and let's rename A as x, let's make it the general x, and B would then be f of x. We plug x into our function f of x and we get f of x. Now down here, if I take the point negative a, negative b, and let's say if a is x, then negative a would be negative x. And if negative a is negative x, and I'm trying to find the y coordinate here, what I would do is I would find f of negative x. Okay, so what have we found? If we have the point x, f of x on our graph, we have to have the point negative x, f of negative x. And what do I know about these 2 points? Well, I know b, from these 2 points, b equals f of x, and negative b equals f of negative x. From negative b being equal to negative f of x, I have negative, and I can replace my b here with f of x. So negative f of x is going to be equal to f of negative x. This is the way we determine if a function is odd. We use this test. And if we can find that negative f of x is equal to f of negative x, and we know that our function is odd. So let's try this. Determine analytically if the function is even, odd, or neither. So to determine if the function is even, where we usually start out at, I'm going to start by finding f of negative x, meaning wherever I have an x here, or I replace it with negative x. Well, negative x squared is the same as x squared. So now I have found that f of negative x is equal to f of x. And if f of negative x equals f of x, our function is even, and we can stop right there and move on to our next problem. I will say there is a case, there's more than one case. There are some cases where you could have a function that's both even and odd. We're not going to consider those too much, but I suggest on your own think about that. Think about what types of functions would be both even and odd. Now let's look at the next function, g of x equals 7x plus 2. Again, determining if this function is even or odd. We start by finding g of negative x. We just plug in negative x wherever we have an x, and we get negative 7x plus 2. We can see that this function, g of x, is not equal to g of negative x, so we know that our function is not even. Okay, so to find Whether it's odd, we need to also find negative g of x. The easiest way to do this is to put a negative sign outside of parentheses that enclose the expression, in this case 7x plus 2, distribute the negative through. We have negative g of x equals negative 7x minus 2. This is not equal to g of negative x. And so what have we found? We found the function is not odd. Our conclusion is that this function is neither even nor odd. All right, and we move on to one more here, where we have h of x equals 2x cubed minus x. Again, we first check if it's even. We find h of negative x by plugging in negative x for x, simplifying. Negative x cubed is the same as the negative of x cubed. And we find that negative 2x cubed plus x is not the same as h of x. So our function is not even. We'll test then if it's odd by finding negative h of x. Again, easiest by throwing the negative in front of parentheses that enclose the expression 2x cubed minus x. Distributing that negative through, we get negative 2x cubed plus x. And we see that negative h of x is the same as h of negative x. And this is how I want to see these problems written out on exams or when you're doing written homework or whatever. I want to see all the steps here. So this function is odd. And we move on. Try on your own. So this is number 2 today. Determine analytically if the following functions are even, odd, or neither. We have f of x equals 3x over x squared plus 1. We have g of x equals the square root of x squared minus 1. And h of x equals the square root of 1 minus x. And next, I'm going to use this same graph for, I think, the remainder of the problems that we have here today. The first thing we're going to do with this graph is we're going to determine f of 2. So to find f of 2, what I'm doing is I'm letting x be equal to 2, and I'm trying to find what is y when x equals 2. So when x equals 2, note we have the point right here. This is the point 2, 3. So when x equals 2, we have y equals 3. So we know that f of 2 is equal to 3 here. And next, I want to solve f of x equals negative 5. This is different. This time we're given y and we're finding x. So if y equals negative 5, there's only one point on our graph here where y equals negative 5, and that is the point negative 2, negative 5. We're trying to find what x is when y equals negative 5. Well, x would be equal to negative 2. So that's our solution here. Now we want to use the graph to find the real zeros of f of x. Real zeros, from a graph, we look for the x-intercepts. So the x-intercepts here, we have 1, 2, 3 x-intercepts. They're the points negative 4, 0, 0, 0, and 4, 0. We get the zeros, which are the x coordinates of those ordered pairs. The real zeros are x equals negative 4, x equals 0, and x equals 4. All right, and moving on. Use the graph to solve f of x less than or equal to 0. So this is where y is less than or equal to 0. This is going to be where our graph, where y equals 0, or where y is less than 0. In other words, where our graph is on the x-axis or below the x-axis. So we have a point here, here, and here where our graph is on the x-axis. It's below the x-axis between these 2 points, right? So in interval notation, my solution is going to start at -4, including -4. It's going to go to 0, including 0. And then union is going to include the interval from 4 to 4. If we write this totally in interval notation. So there we go, and let's move on. We want to find the number of solutions here to f of x equals 3. Well, I'm going to draw the line y equals 3 to help me solve this problem. So here I'm looking for, on this graph, where does f of x equals 3? So it looks like there's 3 different points. We don't need to say what these points are. We just need the number of points. So the number of solutions is 3 solutions here. Well, I'm glad I don't have to figure out what those are because I wasn't sure what this one here would be. So there's 3 solutions. Okay. Now, does f appear here to be even, odd, or neither? Look at the graph. It looks kind of like it's odd, right? It looks symmetric. It looks like if we spun this graph around 180 degrees, we'd pretty much have the same graph. The only problem is this missing point here, and that's going to totally mess us up. So I'm going to say this graph is neither even nor odd, even though it almost looks odd. List the intervals in which f is increasing. So this is something we haven't done yet, and this is in your textbook. For everything else that we're doing in this lesson, I suggest looking at your textbook, reading the definitions. This lesson is long enough. I didn't want to make it any longer, but I'm just going to show you graphically how we would physically find this in the simplified way of finding things. If we go left to right on our graph, f is increasing where we're moving up. So we start moving up, or you can think of where we're walking uphill, because we're going to do some visuals here. So if I'm walking uphill, my writing is really getting bad here. If I'm walking uphill from left to right, starting at x equals -2 up to x equals 5 here, I'm going to be walking uphill and nowhere else. Going from left to right, I walk uphill from here to here. So we're going to, and we use x values whenever we're talking about intervals where things are increasing, decreasing, or a lot of other things. We use x intervals. You can already see that if you kind of look back at some of the stuff we've done today. So from -2 up to 2, our graph is increasing. This is the interval of increase, and it's the only one. There is some controversy among mathematicians on whether we should use a parenthesis here or a square bracket. On a test, you should be correct if you use either one. For now, I'm just using parentheses. In fact, in this particular example, I think parentheses would definitely be more appropriate. Let's look at where the function is decreasing. So if we were walking uphill before, going from left to right, we're going to be walking downhill for decreasing. So and I'm going to change colors so this is a little easier to see. So right here, from -4 to 2, we're walking downhill. And then I don't think I want to use the union sign here because these are, so we're talking about intervals of decrease. So -4 to 2, and we're also walking downhill going from 2 to 4 as in terms of x values, so 2 to 4. Okay, so this is where we're decreasing. We might have a constant function too. So if I had a function that looked, something like this or whatever, we might have a function that's constant on an interval. Let's go on to looking for local maxima. Again, something new. Local maxima is sometimes called relative maxima. Relative extreme values is what we're looking for. Extreme values includes maximums and minimums. So relative or local maxima. For a local maxima, I think if you're on top of a mountain, you're at the top of a mountain, and you can look down on both sides. Okay, there's only one place that, well, we could start here. We're looking for high values for maximums, right? So here's a high value, but we're not at the top of a mountain here. If we went to the left like so, you know, we'd be at the top of the mountain, but we only have one side covered here of our mountain. So we're looking over a cliff or something, I'd say. Here we would almost be at the top of a mountain, except the point's missing. So if I tried standing on top of this mountain, I'd probably fall through. Okay, so there are none here, no local maximum. Okay, let's look for local minima. Okay, so we're looking for low points on the graph here. Here's a low point. And if you think of being in a valley and looking up, that's going to be a way you look for local minima. So right here, we could be in a valley. We could look to the left. We could look to the right. And so I'm going to say I have a local minima. The local minima is local minimum. I knew I'd have to erase that whole thing. The local minimum is actually -5, or you could say y equals -5. The minimum value is a y value. It occurs at the point -2, -5. But the minimum value itself is the y value. Why is this point here not a local minimum? Because if we're in a valley, we only have one side to look up to. We have to be able to look up to both sides of the valley, like so. Okay, so that's local minimum. And let's go on to find the absolute maximum if it exists here. So the absolute maximum is just the highest, or the point on a graph, or the greatest value. And if we're looking at the highest point on the graph here, there is no highest point. It's missing. So here there's no absolute maximum. Okay. Let me just point out before we go on now, let's pretend like this graph extended. Oh, if I can do that. Let's say the graph comes up here and stops. All right. Let me go even further. We'll say the graph goes up here and stops. This point here is not a local or relative maximum, but it is an absolute maximum. So if this was the case, if this graph did here, we could say did go way up here on the left, we would say the absolute maximum is y equals 6. Okay, so we don't have to have a mountain situation to have an absolute maximum. Okay, let's go on. The absolute minimum, if it exists for this same graph, well, we just look for the lowest point on the graph, and it's obviously right here. So lowest, smallest value is going to be the absolute minimum value is y equals -5. The absolute minimum could occur at more than one point. So say, for example, this graph comes down here and it stops here. So the absolute minimum is the minimum. It can occur at more than one place. So anyway, but it's still, there's only one minimum value, even though it does occur at more than one place. Only one absolute minimum value. All right, so moving on, the last try on your own for today, number 3. Determine the following for each of the toolkit functions. So review those. They're in your textbook. Intervals at which the function is increasing, intervals on which the function is decreasing, local maxima and minima, absolute maxima and minima. And that's it for today. So let me know if you have questions about anything.